They say beauty is in the eye of the beholder. And in fact, what we consider to be beautiful in nature, art, or music often differs from culture to culture, nationality to nationality, even generation to generation. But somehow there seem to be constants, commonalities in how we as human beings see beauty. There's a sense of balance, of order to beautiful things. But where does that sense come from? And what does algebra or geometry have to do with it? Can we quantify the beauty of a butterfly? Welcome to the world of symmetry. Crystals, snowflakes, shells, geometric shapes, flowers, decorative arts such as the tilings of the Alhambra Palace in Spain. They all share something besides what we might call beauty. And that something that is implicit in the sort of regularity or self-similarity is symmetry. A symmetry we experience with satisfaction and pleasure in our everyday lives. Often, that which we experience as symmetry is simply the final picture. But how did that beautiful symmetric pattern come into being? With some close and careful inspection, anyone can see that symmetry starts with a basic motif, which is then manipulated in time and space. Mathematicians call such manipulations transformations, or, though this might be confusing, we also call them symmetries, thereby identifying the outcome with the transformation that got us there. For example, start with a basic shape or pattern, say the number 4. If we flip it over like it's on a mirror, we're using a kind of transformation called a reflection. And that reflection creates what we call bilateral symmetry. This bilateral symmetry seems fundamental to nature. We see it in our bodies and in the form of all sorts of living things. Take the butterfly. Its folded wings are the basic pattern. Opening its wings, it performs a reflection, resulting in one of nature's most beautiful examples of bilateral symmetry. But visual symmetries are only the tip of the mathematical iceberg. In fact, there are an uncountable number of types of symmetries. Some we can see and some that we can't. Some having to do with galaxies and others having to do with subatomic particles. Some having to do with magic and others having to do with equations. But in the beautiful visual symmetries that nature and art present, we see everything that we need to know. Symmetry is as much about the final pattern as it is about the motions that got us to that final pattern. And it's the math of those motions that we're now interested in. Remember, we said an object or picture is bilaterally symmetric if we can draw a line through it, what we would call an axis of symmetry. And the two halves are identical in the sense that one half can be overlaid on the other perfectly, with each point finding its exact copy on the other side. Each little fleck and curlicue matched up exactly when I fold the one onto the other. The symmetry that the butterfly reveals and illustrates in opening up her wings is an example of a mathematical and geometric transformation that can be used to both generate and characterize symmetry. It's called a reflection for the way in which it creates an image that would appear by reflecting the original in a mirror. Reflections take place outside the plane of the figure. See how we needed to actually flip our little icon or motif outside the page in order to make the mirror image? Now, there are also symmetries and transformations that take place entirely in the plane of the image. The simplest of these is a translation. Here, we draw an imaginary line above or below our motif and simply slide across that line without rotating or reflecting it. Notice that a translation will be completely described by how far you move and in what direction you move in. Another example is given by a rotation. Here, notice that the rotation is characterized by how much you rotate, as well as the point around which you rotate. The closer the center of rotation, the tighter the curve that the icon traces out. Now, with these three kinds of symmetries, reflections, translations, and rotations, we can generate other kinds of symmetries too. A famous one is the glide reflection, a symmetry that combines a reflection and a translation. A flip and a slide equal a glide. Now, using these symmetries, we can form all kinds of patterns. Let's take a basic motif. We've been using the R, so let's stay with it for a moment. Start with a reflection, then add a rotation, and then maybe a glide. If we follow one symmetry by another symmetry, that is, compose one symmetry with another, we get another symmetry. And what we end up with can be, well, beautiful. We can compose symmetries along one dimension and end up with a frieze pattern. We can even expand the symmetries to cover an entire wall. And if we allowed ourselves to go out to infinity, and that's something that mathematicians love to do, we can cover the entire two-dimensional plane with a beautiful and highly symmetric pattern. Now, as we said, symmetries are both the motions that generate a beautiful pattern like this, as well as the properties of some of these patterns. And when we look at the mesmerizing infinite design, we now see that there are certain transformations in our bag of symmetries that, when applied to the design, bring it right back on itself, like that. So there's a set of symmetry transformations that leave the entire infinite design unchanged, or invariant is what we say. We call this set the symmetry group of the design. Now, the important word here is group. A group is a set of symmetries that behave sort of like the good old integers. Now, what I mean by that is I can take two numbers and add them and get another number. Similarly, I can take two symmetries, apply them one after another, and get another symmetry. I can take a number and find its negative, and when I add those two numbers, I get 0. And similarly, I can take a symmetry, do its inverse symmetry, and it's as if I did nothing at all. Those simple properties define what we mean by a group. One of the most beautiful results in all of mathematics is the characterization or classification of the various possible groups of symmetries of these infinite planar or linear designs that we've been looking at. Now, the former are called wallpaper groups, speaking to these infinite pieces of wallpaper that we've been creating, and the latter are called frieze groups. And while you might think that there are an infinite number of possibilities for these, the fact is that their structure is really highly constrained, and that effectively there are only 7 frieze groups and 17 wallpaper groups. Now, as we've seen, although these groups are finite in number, their possibilities for creating beauty seem endless, and in fact, they've been inspiring magnificent geometric artistry for centuries. This is the Alhambra, a combined mosque, palace, and fortress built in southern Spain in the 13th century. In many ways, it stands as a monument to the ways in which geometry and algebra were combined by Islamic artists as a means of spiritual expression. The ancient religious commandment, "Thou shalt not carve idols for yourselves in the shape of anything in the sky above, or on the earth below, or in the waters beneath the earth," was an injunction against figurative art taken seriously by both Arabs and Hebrews. As a result, they developed a purely abstract and geometric art like that exemplified in the Alhambra. Much of the mathematics we study today owes at least as much to the early Islamic mathematicians as it does to the ancient Greeks. In fact, many of the ideas developed by European Renaissance mathematicians were first developed by Islamic mathematicians 4 centuries earlier. Beginning in the late 8th century at the House of Wisdom in Baghdad, Islamic mathematicians translated the Greek texts, like Euclid's Elements, into Arabic. Islamic mathematicians were interested in both pure and applied mathematics. They used it in astronomy, geography, timekeeping, and even in the legal arena, where they used it to settle problems in the division of inheritances. After the work of Al-Khwarizmi in the 9th century, algebra became a unifying theory. It allowed things like rational numbers, irrational numbers, and geometric magnitudes to all be treated as algebraic objects. That is, abstract symbols that stood in for specific concepts. It is from Al-Khwarizmi that we get the word algorithm, a mathematical process followed by a computer. Omar Khayyam, born in 1048 and mostly known as a poet, was also a mathematician, well aware of the power of combining algebra and geometry. Khayyam wrote that whosoever thinks algebra and geometry are different has thought in vain. Algebras are geometries which are proved. Which brings us back to the Alhambra, with its surfaces covered in repeating geometric motifs, beautifully integrated with poetry carved into the walls. You will say upon seeing it, It is a fortress and at the same time a mansion of happiness. It is a dwelling for the peaceful and the warrior. It is an artistic work that produces wisdom. Whether the Islamic designers of the Alhambra understood the mathematics of symmetry and how is a matter of conjecture. What we do know is that the work of Islamic mathematicians in spatial symmetry and algebra foreshadowed the creation of group theory, a core concept of symmetry. The study of symmetry allows us to look at geometric things using algebraic tools, and that lets us both solve difficult problems and connect things that don't seem to have anything to do with each other. How? It's all about symmetry groups and something called invariance. So symmetry, group theory, the math of beauty actually is what it is ultimately a lot of algebra. And so we're lucky to have with us today Rosa Orellana, professor of mathematics at Dartmouth College, who uses algebra all over in her work. So Rosa, thanks for coming today.
Oh, thank you for having me, Dan.
Well, we've been seeing a lot of beautiful geometric objects and trying to make sense of them algebraically, but let's sort of make it a little bit more rigorous with some good examples, shall we?
We should start with like a rectangle and try to explain the ideas because it's easy to see it there.
All right,
so actually, let's have a square.
Okay, squares are good because squares are highly symmetric.
So now the idea then is that we would want to have a motion in a space that brings us back to the exact configuration that we have.
Okay.
So for instance, here is the square.
Right.
You close your eyes and I do something to it.
Okay.
And you open it and you tell me if I did anything.
Okay.
I can rotate it by 90 degrees.
Okay.
And this brings me actually back to the same configuration.
That's right. Occupies the same space and looks as if I haven't moved space at all.
Exactly. I can do 180 degrees.
Right.
If you think about it, 90, 180,
Yes.
360.
Right.
You can think 180 is 90 plus 90.
Right.
So if I do 90 and then I do 90 again,
Right.
it's the same as if I would have rotated by 180 degrees.
That's right. So you're allowed to compose these moves is what we would say. There's a composition.
Exactly. So this is kind of like when you are doing algebra, you start to realize, you know, can I combine these motions so that I get a similar motion? And in this case, we want a motion that leaves the square invariant the same.
Yeah, and it's interesting to look at. I mean, in fact, the square specifies that there are only particular transformations that are going to leave it alone. Like if I had rotated that thing by 30 degrees, you know, or you did that, I would know you had moved it. Now the square is, of course, very symmetric, we've said, but you know, you can kind of reduce its symmetry, right? I mean, reduce the symmetry of a quadrilateral.